Everyone, my name is Taylor Sparks. I'm the editor-in-chief of IMMI, and I've got a brand new paper to talk about. It's about text mining for process, structure, property, relationships, and metals. The lead author here is Amit Verma. He's at Lawrence Livermore National Lab, but a bunch of collaborators from Carnegie Mellon University as well. Now, this is a subject that's near and dear to my heart. In fact, right here at IMMI, we've published on this very topic on tools for taking data out of the literature and putting them into databases. The authors point out that as we've gone from natural language processing and now into the era of large language models, the ability to pull that stuff out of data is becoming a reality, but there's lots of room for improvement. For example, one of the things that they talk about in this paper is the schema, right? Which is essentially how you're organizing the data, right? There can be general purpose schema, or you can get these really domain specific schemas. And in the past, what we've been seeing is a lot of very domain specific ones. So what they're going to try and explore here says they develop a general purpose schema that's going to be used to try and capture broadly process, structure, property relationships. They're going to test that in high temperature structured materials, as well as sort of uncertainty quantification. And then secondly, they want to explore, okay, is it not just the schema, but which language model? Should you use one that is trained on the domain of material science, like MATBERT, right? Or can you get away with general purpose large language models like ChatGPT 4o? There's some important prior art to recognize here. They point out this paper as one example, right? This paper, published in Journal of Chemical Information and Modeling, points to the real challenge in using general versus domain-specific schemas. Okay, now again, there's lots of different ways that you can organize data as you're pulling it out of the literature. Here they talk about some of the aspects that guided them, right? They say they're going to focus on two aspects. First, the material science specific entities, and two, their interdependencies. So for example, they say a material sits at the top, followed by its synthesis, microstructure, phases, properties, and all the way down at the end, the application that defines it. Well, it says while a specific publication could explore this interaction within an environment or a participating material to understand a specific underlying phenomenon via a single or a series of multiple operations or characterization techniques. And here's an example using the BRAT annotation tool right there. This is showing you the first couple of sentences from some abstract, and you see that there are sort of named entities. There are relationships, whether something is a descriptor, a result, a property, synthesis, participating material, co-ref, right? All these different things are sort of outlined in this schema. So here in the different tables, they introduce the idea of what are the different entity types, right? Whether it's a material or a synthesis, characterization, environment. They're giving you specific examples as well as the definition. And they also have relationships that could exist between these different named entities. So is it a form of, a condition of, observed in, property of, right? They have some nice comparisons comparing their entity labeling mappings or their relationship mappings with other ones, such as the annotated material synthesis mapping. And ultimately, they go about testing this, and they're showing you the actual error, right? They're cataloging it using the F1 score for different variations of using these different types of schemas. Since a key part of this paper is a general use schema, they want to do their labeling in one domain and then actually try it in a different domain. So they go ahead and do that in these high temperature materials, focusing on uncertainty quantification for these materials microstructures. The results are shown here in this table where you're showing you the base performance plus S2 plus T, where that S2 denotes further addition of the partially annotated abstracts from the second stage of active learning, plus T means that they use transfer learning to include annotations from the domain number 1. And basically you can see this slight improvement from the base as you add these additional annotations. The second thing they wanted to test was whether or not you needed to use a material science specific language model or whether you could get away with something sort of general use like ChatGPT. And basically what they find is that both can work, but it says our findings indicate that fine-tuning of a language model significantly improved the named entity recognition compared to the material science domain model BERT. But they point out that if you add information from domain 1 and domain 2, so you're adding additional examples, that the material science domain BERT CRF model can actually match the performance of ChatGPT 4o. There's lots of great takeaways from this. Here's one that I just think is pretty interesting. Ultimately, they're arguing for simplifying the schema complexity. They show that when you simplify the annotation schema by reducing, for example, the number of entity types and therefore the number of relationship combinations that can exist, you're seeing an improvement in the performance. And then with the data, obviously, the amount of data that's going to be necessary for this is going to be highly dependent on the complexity of these models. I hope you'll take a look at this paper and learn more about it in the latest issue of IMMI.